To memorize it and remember it?
Yeah.
Why do people go to school? I don't know.
School's over.
School's overrated.
Never let school get in the way of your education. So guys, go ahead and try to do these two problems. Here's the setup, and then I want you to do these two steps. You can do both of those steps with everything we've discussed so far.
Sans numbers?
Exactly, sans numbers. No numbers, haha. Your favorite kind of fun.
Okay, let's make it people ready.
Yes, exactly.
Okay.
And it's because unit circle 1,
Oh,
if you divide something by its length, now its length goes to 1. Cool. So that's why I call it a good building block. So it's 1, make it 2, then I just double it. Okay.
Professor,
Yes.
going back to when you started out with the box problem, 20 cosine 30 degrees, when you translated that to 10 feet per second, that translation...
Or just $10 per foot.
Yes, yeah, maybe $10 per foot. That first translation, is that just a scalar, or did you translate it to a...
No, it's just scalar.
Okay.
That's why when I try to take that physical representation, put into a formula, I had to use magnitudes because those were really then the magnitudes.
Okay.
$10 a foot had a direction. You would only pay me $10 in this direction, right? And the direction I moved in obviously had a direction. But I just used the length of how far I moved and the length of what he was paying me, $10. Does that make sense? So that's why it has magnitudes in the formula.
So it didn't become an equivalent vector along the $10
No,
per foot?
exactly.
Kind
And
of
that was
like-
the point I was making, that dot product comes out to a scalar.
Right.
In section 11.4, we learned a different multiplication that comes out to be a vector answer, which in a way is more satisfying. Pop. So what do you guys think about the first piece of this? We've actually done that already.
How do you rotate?
Magnitude of u times cosine.
Yeah, it'd be magnitude of u, cosine theta. Right, we've seen that before. The component of u and the direction of v. And again, how many dimensions do these live in? I'm going to ask that a few times, and I kind of asked it earlier. Just because I've drawn them on the board, don't they live in 3 dimensions at least? Because we're in 3 dimensions, just because they are on the board doesn't mean they're, right? And just because we live in 3 dimensions doesn't mean that these don't live in more. So these are, I don't know how many dimensions this is in. So it doesn't matter how many components these vectors have. No. That's my point. How are we doing? At least 2 or else directions out the door here, right? You guys got it with me yet?
So 2 connected vectors will never be three-dimensional. They'll always be planar.
No, you gotta be careful. I really want this understood. If and this is something you guys kind of inherently understand. When you do algebra, everything's in 2 dimensions, right? When you first learn algebra, you do. But we understand that that's actually at least 3. They're just saying the 3rd dimension is always 0. So when I draw that on the board, I'm not designating how many dimensions my u is in. How long is u if I write it out? I have no idea. because I really want you to get this. No matter how many dimensions a vector actually lives in, how long its name is, it really is just one dimension. And if I draw another one, I just need 2 dimensions to represent them. Is that cool? So when we get to lines, a line in 80 dimensions, its formula should be easy. Because a line really has just 1 dimension. If you think about it, you guys kind of with me here? The only thing that makes a vector difficult is if it is not laying on an axis. Does that make sense? If my vectors are all laying on axes, isn't that an easier problem, whatever the hell I'm asking you to do? Because then they're 90 degrees apart and all this kind of stuff. The minute I move it away from an axis, it gets difficult. But is there an absolute universal acceptance of where axes sit? No. I can move the stupid axes, can't I? Right? So if I draw something up there like that, the reason I'm saying this is because everything we do here goes to more than just 2 dimensions. It's however many dimensions. So it's not dependent on 2, 3 dimensions, what we're doing right now. It's however many dimensions you happen to be in. All the math works the same. Because when I draw it on the board, sometimes students get stuck on, okay, that's only 2 dimensions. When is he going to talk about 3 and all that? He hasn't talked about it yet. Well, shit. Screw him. I don't know how to do 3 dimensions then. Yes, you do. This is every dimension. Okay, maybe. So what about this one? Find a vector whose length is the same as 1 that points in the v direction. So what's points in the v direction? And of course I want to multiply that by, I think I heard somebody say, the length I want it to be. So when I do this, it's got length 1. When I multiply that, it's now got this length. So this is officially what we just figured out. This here is the projection of u on v. So what we just figured out, this is the projection of u, good Lord, Jeff, on v. How are we doing? In a way, doesn't that make sense? The way that I love, and of course you do this in physics too, you say, okay, if I shine a light straight down, this would be its shadow. This would be the shadow of u. Shine a light perpendicular to v, and its shadow is the projection. The shadow on v would be the projection. You guys get that? Sort of? So if I put this on here, and I had a light source coming in directly at it, the shadow, that would be the projection of my marker on this, and specifically on this vector here. How are we doing? This piece is old news. This piece is old news. You put them together and you get something new. Math is famous for this. This is the length. This, like I told you very often, is the direction. The unit vector there just provides direction. What's a little confusing about this projection is the symbol we use for it. Not the, thankfully we call it P-R-O-J. So far so good. Projection of u on v. I see the unfortunate part of that. Because if you read it, projection of VU is how you see it, and very often, so all your math will be backwards. And that so sucks when that happens, so don't do that. I always think U's up here, V's down there, so the projection of U on V. Because U is actually stomping on V, whatever the hell makes it stick in your head. How we doing? So what we got right now the projection of U on V is U plus sin theta V V. How we doing? Cool. Now let me do a little playing around with stuff here, because what do I almost see up there that we just talked about that it's still in the same section? Dot product. What's missing right here?
V.
So let me put a V in there. U Now, of course, to do that legally, what do I have to do at the same time? Divide by v. Magnitude, yeah. So what's this then? U dot v. How we doing? Right? And that's nothing amazing. You guys should be over. Well, can you do that? I can do that because I divided by the same thing. Who cares? I almost had an easy thing. There it is. Now it's easy. Now I don't need the angle, do I? Because we know the other way to do dot product. And then notice v, so you get the length of v squared. And then just multiply by the vector v. Do you guys, yes?
How'd you go from the first line to the second?
The only new thing in the second line is I multiplied and divided by the length of v. Do you see that? And the only reason that I did that is because if I can make this a dot product, I don't need the angle then. Why would I not want to have the angle in there? Because the angle is hard to find very often. And instead of doing on the side this whole theta equals cosine inverse of bullshit, let me just put the dot product in there directly and just cut out the middleman. If I don't need the angle to figure out the angle to put in there, I should just be able to do it directly. I don't need the angle, it's in here.
So u dot v over
Magnitude v squared, right? Times the vector v.
Okay.
This is going to end up being like a coefficient of the vector. The book's going to leave it outside, you can bring it inside, whatever. Right? I'll be kind of doing it both ways. I'm kind of used to bringing it in, so if I don't think about it, I might end up with it inside, so just be careful. How are we on that? So, and again, the same thing that's really tricky, I don't care what math level you're in, don't forget the idea that led us here, and then I kind of simplify the equation a bit. Very often we lose the connection between this and what got us there. You guys see what I'm saying? So that's where it was directly from what you guys did. You did that before I said a damn thing about what we were doing. You did this. Most of you. Yeah.
In the denominator, going from the second line to third line, you have magnitude v times magnitude v, so that'd be squared. How'd you go in the numerator from magnitude v to magnitude v?
What is u dot v? Magnitude u, magnitude v, cosine theta.
Cosine.
So I just replace that with what it is. And that's why I multiply by v magnitude on top and bottom, so I can capture the u dot v expression.
Why do we have to do this with U's and V's? They look so similar.
I know. Believe me, I know. So in your homework or whatever, if you want to use different letters, I'm cool with that. I'm trying to keep it the way that you'll see in the book, so that when you go with your notes in the book, they match up. But if it was up to me, and the book was agreeing with me, I'd use X and Y, or I'd use even those, depending on the student. Those are both X's, or those are both Y's. That's awesome. Maybe A and B. There's really no mixing those up. Yeah.
So we will end up with two vectors, or how are we going to go? Because it's
this is what physically, geometrically, or however you want to say it. What is this whole thing? Scalar times a vector. So at the end, you end up with some multiplier, some amplitude, some, how do I want to say this? Some multiplier of this vector. Is that cool?
Okay.
That works. Okay, cool. Which only makes sense. And I kind of purposely drew the easiest case to get conceptually. All the same work works if I had this. Where would the projection of u be? It would still be here, even though v is a tiny little dude, right? Because what's the first thing we sort of do? We make this into a unit vector. So what if v had length 1/2 to begin with? Well, we make it into a length of 1. It doesn't really matter how long. I get the same answer if it was there. For v could be any of those. It'd be the same answer. Because all v really does is give me a direction. Right? Cool. And it really doesn't matter if I was like this. Where's the projection of u on v then?
Negative.
And it's not negative. Because you get two negatives. The length is negative, because it's pointing back. And it's going to be negative v direction. So the two negatives cancel. They kind of reference that in the book if you want to look it over. But that's why I got one formula. I don't have to do two cases. There's just one formula for the projection of u on v. So let me do this. Let me see if you guys are able to do this. What's the formula for, there's a formula for projection of U on V. What's the projection of V on U?
V dot U.
And actually, do you think the dot product matters?
No.
The order, it's got commutativity.
So U dot V.
So be U dot V,
Magnitude U squared.
magnitude U squared.
Times vector U.
And one quick way to make sure you're right is if this is on U, it better be in the U direction. If this is on V, it better be in the V direction. You guys see that? How many U's are in this equation? 1. How many V's are in this equation? 1. Cool. Do you guys kind of see what I'm saying? So it's easy to mix those up because of the unfortunate way they decided to do this. But this is V on U, and that's U on V. Okay. So, let me let you guys try this out. I think this might be the last thing we do. Ever.
Come December 21st, it's not gonna matter anyway.
I know. What are you guys even learning this stuff for? I mean, my mind goes through this client laughing at this. You told them. Have you seen John Cusack's crazy silly stupid movie? 2012. Not, was he in Knowing? Has anybody ever seen that movie, Knowing?
Yeah.
Yes, when it's Nicolas Cage.
Oh.
Are you sure that is quick?
I've
What is
seen
It's
that?
an awesome movie until like the last 7 minutes. And then became the worst movie I've ever seen. It's like my top 3 best movies until the last 7 minutes. And I'm like, that's the worst movie. Just to warn you, I haven't seen that. You're thinking about it? Oh, sorry.
Not bad.
Oh, sorry.
Nicolas Cage and we get spoilers so we don't have to research on seeing it.
Actually, it's funny. Somebody who reviews movies, they call it their Gattaca condition, because supposedly that I had never actually seen that movie, but supposedly the end of it was so bad it just killed the movie. So that when they were reviewing this, they said, "This is that. The end of it screws the whole thing up."
Like Gattaca's in it.
I guess Gattaca has a bad ending. People would argue like Waterworld, but that has.
His brother, it goes to Mario.
Alright.